Well, hi again, this is Bob, and we're getting ready to take a look at 6.4, which I believe is the last lesson or section in Chapter 6. This particular lesson is just another application, if you will, of the normal distribution. And another way I'm saying the normal distribution, I sometimes refer to them as our z-tables, or are just our plain old bell curve. Okay, and in order to understand, the best way to understand what's going on with 6.4 is to go back and just take a quick look at 5.3, in which they introduced the binomial distribution. And briefly, you may recall we had a formula. We used the formula for a while until they told us that there's some binomial tables that we can use. Okay, so you know, we use this formula if we flipped a coin 10 times and we wanted the probability that exactly 6 heads came up or something like that. Okay, so this is our sort of our touch point for this particular lesson here. And now what they're telling us that under certain conditions, which I'll discuss in a minute here, is that we can take this entire formula here, which they already gave us some tables to shortcut it, and we can find out answers using our z-tables, which are another name for our normal distribution. Okay, so again, as always, I expect you to read over the material, especially on page 354, but the questions that we're going to see and the questions we're going to do in homework are just formula driven. There's only one thing that we have to recall when we're using our z-tables or normal distribution tables in lieu of the binomial tables or the binomial formula, and that's a little correction for continuity, and that's explained on page 355. Okay, so the first thing I'd like you to do before we even get into this is what they've shown on page 355. It's got a couple of histograms there, and one of them is for, it's a binomial distribution when we have a sample or an N of 10 and a probability of 0.3. And notice how they've drawn a bell curve over that, and it is kind of bell-shaped curve, but it tails off or it's skewed. And then look at the second one drawing there, or histogram, where they have N equals 10 and P equals 5. That particular graph seems to be symmetric at 5 there, which would be like our mean, and it looks like the bell curve approximates it. And of course, it wouldn't take too much imagination to say that the greater number of trials that we had with a probability of 0.5, that graph gets closer and closer and closer to the binomial distribution, gets closer and closer to our normal distributed, our z-tables or normal distributions. Okay, so the idea is here that we're going to use some of the formulas that we used in 5.3, but instead of using this formula, which I'm going to put an arrow on here, we're going to use our z-tables. And a little bit of review from 5.3, if we're going to use the binomial theorem, there must be, recall there must be a fixed number of trials. The outcome of each trial must be independent. You know what? This is stuff that we did. The simplest one would be like head or tail, male or female, when we're talking about children in the family, or we're taking a test and the two possible choices are true and false. Okay, So there must be a fixed number of trials. The outcome of each trial must be independent. Each experiment can have only 2 outcomes, or that can be reduced to 2 outcomes, and the probability of success must remain the same for each trial. Okay, there's a review of 5.3. Okay, and if you have, hopefully you'll recall 5.3, but remember we're going to have a different approach to solving the questions now. And they also tell us to recall that a binomial distribution is determined by the number of trials and the probability of each trial. So those are important items also. Okay, and you may recall that we had a formula for the mean, which was NP, and we had a formula for the standard deviation, which was the root of NPQ. Okay, so then they go on to tell us here that, excuse me, they tell us when P is about equal to 0.5, and we have a number N, we have an, I've lost my place here, and as N increases, okay, they tell us that the shape of that graph or that distribution approaches our standard normal distribution. Okay, so that's what they're trying to show over on page 355. So when we're around a probability of 0.5 for a binomial situation, and as N gets bigger and bigger and bigger, we approach the standard normal distribution. And of course, those are the kind of questions we're going to deal with in this section and the kind of examples. But then they also tell us directly below that when P, our probability, is close to 0 or 1, that we don't get, and N is relatively small, that we don't get a situation where the normal approximation or our normal tables, standard normal distribution could be used. Okay, so what we want is we want a situation where probability is equal to 0.5 and our N is increasing, or said differently, large. In that case, we can use our normal distribution or our z-tables. Now, there's a stipulation here. I'll ask you to finish up with the reading, but they tell us in one quick way to know whether we can use the normal tables or normal approximation to the binomial distribution, and this is about halfway down. N times P must be greater than or equal to 5, and NQ greater than or equal to 5. So we're going to check that on each situation. And then the final thing they tell us is recall that the binomial distribution deals with discrete variables, okay? In other words, head or a tail or male or female. It's a discrete distribution, as you can tell over on page 355 by looking at those graphs. And recall that when we're dealing with the standard normal distribution, I'm just going to write normal. The normal distribution is a continuous distribution. So that's why we need to make a continuity correction. And it goes all the way back to chapter 2. And what we're going to basically have to do for our mean or our standard, or excuse me, what we're going to basically have to do is back off or add 0.5 to the value in question. Okay? In other words, we normally have, if they give us a situation where we want the probability that our our, let's say we're dealing with the number of heads for a given number of flips of a coin or something, and we want to know the probability of getting exactly 8 heads. Well, this is a discrete, and we know that our normal distribution is a continuous distribution. And so what we would basically do, and all of this is summarized on the bottom of page 355, is we would back off 0.5 and add 0.5 to 8. In other words, we would get a continuity correction of x greater than 7.5 and less than 8.5. And then we would find that particular area using the standard normal distribution. But I'm getting a little bit ahead of myself there, but that's the idea. And notice that we've got a correction for every possible situation. Okay, and this is what they're showing on the bottom of page 355, and I'll be showing on my examples. If the probability of x equaling letter A, that's a number there. I believe that's an A. My eyes aren't as good as... Well, I'm going to assume that that's an A. And it says what we do, as I just showed, is we back off 0.5, and we, I'll write it like the book did there. All right, and I'll do one more here. Let's say it's the probability that given x is greater than or equal to, no, it's just greater than A. Then it tells us what we do is this is equal to the probability of x greater than A minus 0.5. Now, we haven't done anything yet, so this might look a little involved, but it's really not. We have two formulas. Mean equals NP, and standard deviation equals the root of NPQ. And when we use those formulas and our corrections, we're going to be able to find a requested area, and that area should be really close to what we would have calculated using our binomial formula. Okay, so before I get into any more theory here, theory can bog us down sometimes, let's just take a look at the top of page 356. Oops. All right, and over on the top of page 356, there's a little procedure table there. And it tells us the first thing that we do whenever we're asked to use the normal distribution tables in lieu of the binomial formula is first see whether we can use the the normal distribution. And recall we do that by seeing if NP or NQ greater than or equal to 5. Then it says find the mean and standard deviation. Remember, the mean equals NP, standard deviation equals the root of NPQ, Q being failures. Write the problem in probability form using our X. Remember, we normally did the probability of X equals something. Okay, and then put a continuity correction on it. And you're going to do that by adding or subtracting 0.5 like we did in chapter 2 for continuity. In other words, we'll just refer right back to the table on the bottom of page 355. That's table 6.2. Okay, and then find the corresponding z-value and then find the solution. All right. Well, this is an important piece of information for our class, knowing that we can use the normal distribution in a binomial situation. but I wouldn't say it's the most important thing that we've run into, like the Poisson distribution or the hypergeometric distribution. It's nice to know about them, but it's unlikely unless you're taking other statistics class, then you'll see them or use them frequently. Certainly we use the normal distribution all the time, and there'll be a number of occasions where you use our other tables that are coming up also. Anyway, here's the perfect, I've got two really good examples that we can do here. Actually, we may just work all of the examples, but the first one is example 616. And it's falling asleep while driving, and it says that 25% of drivers have fallen asleep at the wheel. That's our probability, by the way. That's a scary number. If 200 drivers are selected at random, find the probability that 62 will say that they have fallen asleep while driving. Okay, so then our what we're looking for here is our probability of X, and that's equal to 62. All right, now remember, if we're going to do this question before, you either have fallen asleep or you're staying awake, and Q would be 0.75. Okay, but we're going to follow their example here, and the first example is to make sure that we can use the normal approximation. In other words, our z-tables. And notice that N times P would equal 200 times 0.25, that's basically a fourth of 200, or 50. And of course you can see that NP equals 150, or excuse me, NQ, I'll just shortcut it to 150, and of course 50 and 150 are both greater than or equal to 5. So instead of working this out the long way, we can use our normal distribution, because our first step 1 in the procedure table has been fulfilled. Okay, then the next thing that we do is our step 2 is find the mean and standard deviation. And remember that the mean equals NP. Actually, we already had this. Okay, and then our standard deviation in PQ, I'm going to take the book's word on that, is equal to 6.12. All right. Now, again, what we're going to do is, and our probability, in probability notation, we want the probability that X would be 62 drivers out of 200 fell asleep. Okay, now, this is, if you go back one page to page 355, remember when if we're going to use the normal distribution instead of working the problem the long way, there's a continuity correction here. And we're supposed to add and subtract 0.5 to our X. So if you look at the very bottom of the page, you end up with a drawing that looks like this. I'll have to exaggerate a little bit. We have, remember our X was 60, probability of X was 62. And when we add and subtract 0.5 to that, we end up with X greater than 61.5 and less than 62.5. Now, the whole deal is the area between 61.5 and 62.5, where we have put our correction on, this area would be that probability, that decimal, or that amount of area should be extremely close to the area or probability we would get if we used the binomial formula or a binomial situation, as the whole point of this is. Okay, so notice what they do then. They figure out the two z values, and I'll set the first one up. The first z being for 61.5. Book calls that Z1. Oh, I forgot to put our average there. Remember that NP was equal to 50. It was 200 times 0.25 or 50. Okay, so for our Z1, it would be 61.5 minus 50 over our standard deviation, which was 6.12. And that gave a z-value of 1.88. And I'm just going to write the second one because we're really more interested in the application here. The second z-value turned out to be about 2.04. So now we're in this situation here. I'll replace where I had the values before with our z-values. Okay, and remember, those are with our corrections, okay? Where the 1.88 before turned out to be 61.5, and where the 2.04 is turned out to be 62.5. This area here is going to be equal to our probability, which would be equal to the answer had we worked this out with our binomial formula. And they tell us that that area there, this is step 6, they go ahead and do their corrections. They go ahead and do the calculations, and they get a probability of 0.94. %. Okay, or about 1% then of would the probability that exactly 62 drivers would have fallen asleep based on the information they gave us is around 1%. Okay, now that's the same answer we would have gotten if we would have used the formulas introduced in back in chapter 5. Okay, well, the main thing on these questions is our correction for continuity. So let's go take a look at another one. I'm going to ask you to take a look at the one with ragweed allergies, and I'm going to go work 618, example 618. This one has to do with batting averages, and it says if a baseball player's batting average is 320, 0.320, find the probability that the player will get at most 26 hits in 100 at bat. Okay, so the first thing we've got and I've lost my pen here, which is not good. Okay, and then the next thing we know is n is going to equal 100. at bats. And that means that intuitively we can see that if a batter gets a hit 32% of the time, that we would expect him or her, whatever the situation is there, to get 32 hits at every 100 at-bats. There's nothing that doesn't follow from that. Okay, so the next thing that we need to find out, recall, is whether we can use our normal distribution to approximate the binomial formula. And remember that if P is equal to 0.32, then Q would equal 1 minus 0.32, or 0.68. Now, what we're doing is that step 1 in our procedure table to make sure that we can use our formula, or our normal distribution tables. And so we're going to have a total of 100 at-bats, okay? So is it true that 100 times 0.32 is greater than or equal to 5? That's equal to 32, so certainly that's true. And P in Q would be 100 times 0.68, and that's certainly greater than or equal to 5. So we have verified that we can use our normal distribution tables. All right, then the next thing that they tell us to do is find the mean and the standard deviation. You can follow along with this. The mean is in P, and that would equal 100 times 0.32, or 32. And our standard deviation this should be somewhat mechanical from what we've done before, equals about 4.66. Okay, well, the next thing that we do is our probability. The way the question is phrased, it says find the probability that the batter will get at most 26 hits. Well, if you were graphing that, we have to go back a little bit, at most 26 would be 26 or less, and it would look like this on a number line. Okay, so that's what we're looking for, and we have to remember that when we're dealing with a binomial situation, that is a discrete situation. And if we're going to use, or the purpose of this lesson is to let us know that we can use the normal distribution tables, then we have to make a correction for at most, okay? And another way of thinking of at most, I'll write on the top of the next page here, would be x less than or equal to 26. Now, go back one page, and, go back 2 pages, and on page 355, we have a correction. It's number 4, and it says the probability for a situation where x is less than or equal to a, it says we simply add 0.5 to our value a. This is number 4. So what we're really going to be, that was rule 4 on page 355. So instead of finding the probability of x less than or equal to 26, when we put our continuity correction on it, it turns out to be x less than 26.5. All right. Well, we're now ready to go. Here's the situation graphically. Here's the expected number of hits, or the mean. It was 32. Here's what we're trying to find the probability of, 26.5. And remember that it said at most 26 hits. And here's our continuity correction. So what we're looking for is this. Phrased differently, what's the probability that the batter will get 26.5 hits or less? Okay, and you can see how they turned that into a z-value, which normally a binomial situation, because it's going to get a hit or not get a hit. It's two outcomes. They end up with 26 point, I lost my pen there. 26.5 minus 32 over our standard deviation of 4.66. And our z-value equals minus 1.18. Okay, so the last thing that they do, and I'll turn this back into z-value terms here, is they find that area that's associated with minus 1.18, and it turns out that that probability, or that area, is equal to 0.1190. And that gives us a probability then of getting less than that number of hits. Remember, that's back in our normal usage. I've written that as the question originally stated, even though we had to put a continuity correction on it, and that turned out to be okay, 11.9%. Okay, well, the last thing I'd like you to do is take a look at example 619. And I'll work part of this problem with us just so we go back and tie everything together. Remember from our formula, they're going to give us a situation where n is equal to 10 and p is equal to 0.5, and we would go back, and there's two ways to do this, of course. We can go back into our tables, or we can use our formula for an x is 6. If we used our formula, I'd like to tie everything in together as best I can. Okay, if we used our formula, we would have gotten the answer of, I could just go back and look it up real quick, but it would be 0.205. Okay, that's calculated, and from our binomial table, we shouldn't be surprised that we would get the exact same answer. You can verify this. Okay, now notice what the book does, and this is where I'm going to close off here. They went ahead, and where they had, we would expect, you can follow their calculations. If you flip a coin 10 times, we would expect 10 times 0.5 or 5 heads to come up, and we wanted the probability of getting 6 heads. Well, of course, they have to put a correction on that when we're using our normal distribution tables. And so what we would be looking for is this area between 5.5 and 6.5. And I got that correction from flipping back a couple of pages on page 355, and the probability of x equaling a, we had to add and subtract 0.5 to our random variable, which in this case was x. Well, notice I'll leave the calculation to you to follow their calculation, but notice what they got. They got by using the standard normal distribution tables, they got an answer of 0.2034. Well, that is pretty close to 0.205. Okay, in fact, it's only like a few 10,000ths of a unit away there. The first two decimals are important, 0.20 and 0.20. So that third place was a 3 rather than a 5. Okay, so what we should be convinced of now is that if the situation warrants it, we can use the normal distribution tables to find the probability of a binomial situation. But we have to make a continuity correction. Okay, as I mentioned at the beginning of this lesson, this probably isn't the most important lesson that we'll see, but it is important from an awareness factor that we're seeing another use of this normal distribution. Okay, well that does it for chapter 6. I will give you a couple of questions like this in the homework, and you might have a quiz question on it, but I don't think we'll be running into this type of question on a test. And I will be back shortly with some thoughts on the first lesson in chapter 7. Thank you.